This video is on simplifying radicals. So you can go ahead and pause the video and fill in your blanks. So the product rule says you can multiply radicals as long as they have the same index. So the numbers inside the radical do not need a match. Just the index number here have to be the same. And when they are, then you can multiply the 2 times the 4 and get 8. And then if it's possible to simplify or evaluate this is saying what times itself 3 times is 8, and it would be 2. So just like with fractions, we can look at a fraction and know if a fraction is in simplest form. So for example, if we had the fraction 4/8, it is not in simplest form because the rule is see if there is a common factor that divides both of these. So if we pick 4, we would be done in one step. Instead, if we were to use 2, which is not the GCF, we would then have to simplify once more. Same thing goes with radicals. If we don't pick the highest number, when I tell you the steps, you might have 2 steps like we have here. So just like we have rules to know if fractions can be simplified, we have rules here to know if radicals can be simplified. So let's go ahead and take a look. For a radical to be in its simplest form, the expression inside the radical cannot contain any factors raised to the index. So let's talk about what that means. That means if the index, if we take a look at example 1, we are asked to simplify the square root of 12x to the 5th. So let's go ahead and just focus on the square root of 12. So what this is saying is we have to look and see if, since this is a square root, we would make a list of all the perfect squares. So 2 times 2 is 4. 3 times 3 is 9, 4 times 4 is 16, right? So that's how I'm making this list. I don't need to memorize it. I would just write it down on a separate sheet of paper, and then I would have it when I'm working with simplifying radicals. 5 times 5 is 25, so on. So I have created a list already. These are all the perfect squares. So what we wrote up here pretty much says if any of these numbers can go into this number here, then it is not simple in its simplest form. So because 4 can go into 12, then we can split it up and we can write it as the square root of 4 times the square root of 3. And because the square root of 4 is on this list, it has a perfect answer. It's 2. What times itself twice is 4? It's 2. And then we would take a look and ask ourselves, can any of these numbers go into 3? Since the answer is no, then we know this one is completely simplified. And now we have successfully simplified the square root of 12. Okay, the other method we could use, we take the 12 and we don't use the list. We could pick whatever numbers we want and we would make a factor tree. So for example, I could pick 6 times 2 if I want. I could also pick 4 times 3. Pick whatever 2 numbers you want as long as they multiply to the given number. So again, it doesn't have to be a number on this list if you're going to use method 2. And then you're going to keep going and make a prime factorization tree. So I'm going to circle the number when it's prime. Remember, prime means the only number that goes into it is 1 and itself. So now I'm going to keep going here because 2 times 3 is 6, and then both of these are prime. So I know this is going to sound corny, but think of this like a jail, the radical jail. To escape, it needs however many to team up that is the same as the index here. So since the index here is 2, I need 2 of a kind. So this one and this one match, but only one of them is going to make it out of the jail alive. And then we have this poor 3 here all by itself. So we still get the same exact answer. It's just a different method, different way to look at it. It's really the same thing because 2 times 2 is 4 and the square root of 4 is 2. So that's like why it may feel like you're doing it different, but it's really the same thing. Now let's talk about the variables, how to do the variables. So I'm going to first draw a picture. We're not going to want to draw a picture for all of them because the exponents could get a little bit higher. So let's think of the jail analogy as we do this one. So since the index is 2 here, I'm looking for 2 of a kind. So these 2 here, but only 1, so if this is the jail, only 1 makes it out of these 2. And then these 2 here, again, only 1 makes it out. And then you have this 1 left here. So we'd have x times x, so that would be x squared left in the outside of the radical, and just an x in the inside. And that would be our final answer. So we're not going to want to have to draw this. I wanted you to see the visual of what's going on. But when we group things into groups of 2, that's the same thing as just dividing by the index. So instead, all we have to do is take the index, which was 2, and divide it into 5. And that would tell us 2 goes into 5 twice. That's the 2 groups. And then the remainder is 1. And that's how we know how many are left inside. So that would be the fast way to do it. So that's exactly what I wrote up here, that the remainder stays inside. And you never want the exponent inside to be greater than the index. So since this 5 here is greater than the index, that's how you know just by looking at it that it could have been simplified. All right, let's go ahead and try another example here. So the difference between method 1 and method 2. Method 1 uses the perfect square list. So you need to pick a number on this list that can go into 80. If none of them do, then it's as simplified as it can be written. So I know that 4 goes into 80, but 16 also does. So if I pick 16, 16 times 5 is 80, and then the square root of 16 is 4. And we're done in one step. Now, if, let's say, instead you picked 4 times 20 instead. The square root of 4 is 2, but the square root of 20 we can keep going because it is not simplified. Because a 4, I could split this into the square root of 4 times the square root of 5. So then we'd have 2 times another 2, which is 4, and then radical 5. So we still get the same answer, it just had an extra step because we didn't choose the greatest perfect square. Okay, whereas method 2, we don't have to pick a number from this list. We'd pick whatever number we want. So if we want to pick 8 times 10, we could. And then we keep going until we have all prime factors. Okay, then again, I know it sounds kind of corny, but think of this like a jail. To escape, we have to have whatever the index is, that many of a kind. So since the index is 2, we have these 2 match, but only 1 will make it out. And then these 2 match, but only 1 makes it out. And then we have this 5 left. So we would get 4 radical 5, which is what we got here. Now, as for the index, again, I'm going to make it visual for one more here. We'd have 1, 2, 3, 4, 5, 6, 7, because it says x to the 7th. And then since the index is a 2, I need groups of 2. So there's only 1 left inside. And then there would be these 2 escape, but only 1 would make it out. These would escape, but only 1 survives, and these 2, only 1 survives. So you would have x to the 3rd power, and then x in the inside, and that would be our final answer for this problem.